Alright, chapter 9 is going to deal with chemical quantities. Now, in previous chapters, we actually saw how we could use a balanced equation to show us what's all going on in a chemical reaction. Like this one, for instance, we would see that when it's all balanced, I'm going to have a 2 here and I'm going to have a 2 there. Because that gives me 2 carbons, 2 oxygens plus another 2 oxygens gives me those 4 oxygens. So our balanced equation shows the relationship between a molecule and its other components, or the moles and its other components. So it gives us a relationship between the oxygen per se and the CO2 in this reaction. That is what we're dealing with in this chapter. We're going to actually take that a step further in the balanced reaction and use stoichiometry to talk about the amounts. And it's not just going to be moles like there. We're going to actually be starting with like grams of the oxygen and grams of CO2 being produced. So all the calculations will actually go to the mole because that is where it's all calculated. But that's what we're going to be looking at in this chapter. Alright, so right off the bat, can we actually relate grams of C18H or C8H18 octanol to CO? Not yet. Now, reason I say not yet, even though those both have carbon, we have no idea what we're talking about with regard to these. It could be a reaction where the octane, the CaH18, is converted totally into carbon monoxide. But we can't relate them as it's worded here. So the answer here is no. What we will need to relate a compound A to compound B is a balanced equation. Reactants going to products. And in this case, it would have to have CaH18 and CO somewhere in that balanced equation. They can both be products, they can both be reactants. One can be products and one can be reactants, but they would both need to be in the balanced equation for us to be to relate them. Alright, that is stoichiometry. We are going to actually follow these steps to actually get our all these calculations in this chapter. So when we talk about stoichiometry, what we're starting with always is a balanced equation. Sometimes we'll have to write out the equation, sometimes we'll have to write it out and balance it, sometimes that will be given to us. Alright, once we have that, and we have a relationship between compound A and compound B in that balanced equation, we can actually start with that. Very first thing we're going to do is if I give you something that's some units other than moles, you will convert those to moles. Third step's interesting. We'll talk about more about limiting reagent later on, and then we will actually use the balanced equation to give us a stoichiometric ratio or a conversion factor. And then the last thing, our conversion at this time will be always in terms of moles, but we might want some other unit, like grams. Alright, so what do I mean by that? Let's think about this particular reaction. Now, if you see, I only gave you the reactants, C3H8 and O2, and I want to know how many moles of propane would be required to react with 3.2 moles of oxygen. Well, if that reaction was going to be left like that, that's implying that there's one C3H8 and one O2. So if it requires 3.2 moles of oxygen, it would require 3.2 moles of propane because it's a nice one-to-one relationship. But the entire equation's not balanced. So the very first thing we actually need to do is we need to balance that equation. Alright, so we have C3H8 and oxygen. This is a combustion reaction. Most combustion reactions have CO2 as a product and water vapor. All the carbohydrates, or hydrocarbons, CHs, form CO2s and H2Os. The carbons all turn into CO2s, so we have 3 of those. There are 8 hydrogens, so we're going to make 4 waters. And then we're going to have to add a lot of oxygens to balance that all out, because I got 6 O2s, and I have 4 oxygens, so I have 6 oxygens, 4 oxygens, I need 5 O2s. Okay, now that 5 and implied 1 is going to be a conversion factor when we all put this down. So We're giving 3.2 moles of oxygen, and we want to know about propane. So we need a relationship between propane and O2. We're going to generate it from a balanced equation. There's 1 here, there's 5 there. So to actually get the answer here, the number of moles propane required, we're going to take that 3.2 and just divide it by 5. And we get that this is going to need 0.64 moles. Now the second one wants to know amount of CO2 that's produced, carbon dioxide. Had we just started with that equation as it was written, we wouldn't have any idea how much it's produced because we needed to balance the equation first. But once it's balanced, I can take those 3.2 moles of O2 and I just do another conversion factor. I'm going to take those 5 O2s and convert them into 3 CO2s because that's the number in front of it. So, excuse me, 3.2 times 3 divided by 5 is 1.92 moles. Now technically that's what we're going to do in this entire chapter. We're just going to expand it because more often than not we're going to be using grams rather than moles because grams is something we can actually get on a scale. Moles is not something that's easily just derived by any instrument in a chemistry lab. Alright, so let's practice that on a couple more. What am I missing here? Actually, it's supposed to be on this slide. I don't know where it went. But in your actual test, there's going to be a lot of times I'm going to give you the balanced equation. And I did mean to give the balanced equation on this one. So I got 1 carbon, 1 carbon. I need 2 of these, and I'll need 2 of those. All right. Now that we have a balanced equation, all we need to ever do is focus on what I gave you and come up with a conversion factor using the coefficients in the balanced equation that show you a conversion from what you had into what you want. And it doesn't matter the components. So down here, 3.61 moles of CH4. If I want O2 instead, it's still going to be the 1 CH4 because there's a 1 implied there, and it's 2 O2s. So the conversion factor is 2 to 1, 2 to 1. So they look like they're the same thing, but they're not. The 2 is because the O2 number. And let's see, this is going to be 7.22. Bad idea doing that in your head when you have a calculator. Oh, I should have trusted it myself. I do need to make my 2's look better though, don't I? That looks terrible. Ooh. If you didn't pick up on that, I'm having a weird little computer glitch there. Alright. More often than not though, we're going to give you masses. If you notice this one, it says 48 grams of oxygen. And the oxygen is O2 here. Well, we are going to do the exact same type of idea. We are going to end up using that balanced equation to show the relationship between oxygen and carbon monoxide, what we want. But before we do that, we need to convert our mass into moles. We need to know how many moles of O2 are in that 48 grams. We're backing up here to what we actually introduced a few chapters ago with molecular weights. And turns out the molecular weight of oxygen is 32.00 grams. Now once we have that in moles, now we can use our balanced equation that shows every oxygen, it's implied to be 1, would need 2 carbon monoxides according to this balanced equation. And then I'm going to do one more conversion because it does want mass of carbon monoxide. So 1 mole of CO, 12.01 plus 16 molecular weight of oxygen is 2801. Now, the moles there would cancel, CO2 would cancel, we'd end up with just grams. And in the calculator, it's going to look something like this. Let me clear this out so we see it. 48 divided by 32 times 2 times 28.01. We get a mass of carbon monoxide of 84.0 grams. All right, let's do another one. Now, first step you're always going to need is a balanced equation. So we need to actually come up with a balanced equation. So it says how many grams of magnesium hydroxide are needed to react with HCl. All right, if we back up a lot, we're going to see that this is a neutralization reaction. The acid and the base are going to react together. And since there's 2 OHs here, I know I'm going to need 2 of these because the H and the OH are going to form water. Because that's what a neutralization reaction is. We got a base here and we have an acid here. All right, that's going to leave us with magnesium and chloride, the salt from a neutralization reaction, which in this case is MgCl2. I get that because Mg is a positive 2 ion, chlorine is a negative 1 ion. All right, we want to know how many grams of magnesium hydroxide are needed reacted to with 1 gram of HCl. 1 gram of HCl. Very first thing, I need to convert that to moles. I've got my periodic table right here. 35.45 is the mass of Cl. And that, 1.008, is the mass of hydrogen. So this is 36.46. Our balance equation shows that we'd have 2 HCl's for every 1 MgOH2 and 1 mole of MgOH2 is clear. I keep hitting the wrong buttons. O, oxygen, hydrogen. That would be the mass of an OH. That's the mass of 2 of them. And then I'm going to add to that the mass of a magnesium ion, magnesium atom, 24.31. 58.33. And our calculation will look something like this. 1 divided by 36.46, also divided by 2, times 58.33. Excuse me. I'm going to need 0.7, was that 2 nines? Oh, 7.79999, so 0.800 grams. All right. Excuse me. This one I give you a lot more steps, so this would be a little bit more realistic if I want you to determine an equation, because I'm actually telling you all the components. So we have silver carbonate decomposing into 3 products: silver, carbon dioxide, and oxygen. So Ag2CO3 turns into AgCO2 and CO2. Okay, to balance this out, I'm going to start with a realization that I have more oxygens already on the product side than I have on the reactant side. I'm going to start by doubling the reactants. All right, now I'm going to try to balance it. So I have four silvers. That is 1 carbon for every silver carbonate. So there's 2 CO2s because I have 2 silver carbonates. And now at this present moment in time, I've got 6 oxygens. I have 4 plus another 2. It is now balanced. All right, once we have a equation balanced, we're ready to actually do the same 3 conversion factors we did before. We need the molecular weight of the silver carbonate. We will relate our silver carbonate, what we had, into what we want, and then we're going to convert that into grams using the molecular weight. Now that one I know because we've done it before. But I need to calculate the molecular weight of silver carbonate. So silver, element 47 on your periodic table, has a molecular weight of 107.87. And there's 2 of those. We're going to add to that a single carbon and 3 oxygens. And we get a molecular weight of the silver carbonate of 275.75. And then we do a calculation very similar to what we've done in the past. That laughter there was, I have a cat just jumped on the computer here. So we get a mass of 13.9 grams. I guess that'd be 14. There's only 2 significant figures in how that 240 is written. So it should be 14 grams for an answer. All right. So that's how we're going to handle this. So make sure we balance our equation. Any units for anything that I give you will have to convert to moles. Now right now it's mainly going to be around grams, so you'll be actually converting to moles using the molecular weight of either the atom or the molecule. And then use your stoichiometric ratio, which is based on that balanced equation. Okay, next little thing we're going to do with this. What causes a reaction to stop? Typically, you use up a reactant. There are certain times we stop things differently, or it seems to, but your car burns oxygen to make CO2 and water. And how do you stop it? Well, we turn the ignition off. Well, how does that actually stop the car? Well, technically, it stops feeding gas into the carburetor. If there's no gas, doesn't matter that there's plenty of oxygen around, it will stop simply because of that. So it's not so much that reactant is used up, it is technically used up in the engine, but that's simply because you stop putting it in. But that's actually what typically stops a reaction, is you use up one of the reactants. Alright, that creates a nice little dilemma. There are going to be times when you only use up one of the reactants. Your car is a good example. It's very unlikely that a car stops because it runs out of oxygen, because there's plenty in the atmosphere. Now, if you were to do something silly, put your car in a garage, close the garage door, and fire it up, it will eventually run out of oxygen, and the car will stop. But it also fill up the garage with carbon monoxide, be very dangerous, very, very, very bad thing to do. But it would actually stop eventually because it runs out of oxygen. But It's much more likely if you ever see a car on the side of the road that stopped because of something like that, either mechanically broke or ran out of gas. All right, so what we're talking about is a limiting reactant. And very simply, if I just have a very simple reaction, A plus B going somewhere, one of these could be in excess or a larger amount than what you need. The other one would be the limiting reactant. It's the one that's going to run out of first. We've done the calculations before, assuming that the other reactant wasn't a factor. But what if I give you the amounts of both A and B? How do we know what's going on? How do you know what's going to make the actual product? Well, we have to look at those stoichiometric ratios, and we have to do the calculation twice, technically. All right, let's do one of these just to see what we're talking about. I got a bunch of terms here, but let's just go right to one. So I have carbon monoxide and oxygen going to carbon dioxide. I have that equation again. And I say we have 3.2 moles of oxygen and 4 moles of carbon monoxide. Now looking at that, you might say, well, the 4 is going to be going to last longer because it's a bigger number. But that stoichiometric ratio is 2. So we're going to use it up twice as fast. All right, much more easy way to see what's going on here, I think, is to actually compare the species together. I'm actually going to do just one calculation. I'm going to take that 4 moles of carbon monoxide, and I'm going to look at the stoichiometric ratio between the carbon monoxide and the oxygen, the other number I gave. And it's a 1, so 4 divided by 2 is 2. So what that calculation tells me is to use up all 4 moles of carbon monoxide, I would need 2 moles of oxygen. Well, do I have 2 moles of oxygen? Yeah, I actually have 3.2 moles of oxygen. So since I have more here than what this calculation is, this one's in excess. And this one is limiting. So if I wanted to calculate how much CO2 is being produced, I would want to use the 4 moles of carbon monoxide because that's the one that is limiting the results. We're going to run out of it first. That's what it's talking about in all these words. The limiting reactant is the one that runs out of first. Sometimes you'll have to do 2 calculations, but if you actually are like this and we just need to know which one's the limiting reagent, we can just do one calculation and just compare it to the other. All right, so let's do this one. What is the limiting reactant if you have 10 grams of hydrogen and 40 grams of oxygen in this reaction? Now, you notice how these are both masses. All right, makes it a little bit harder. All right, but we're just going to take one of those two. And since 10 is the first number, I'm going to use it. So I have 10 grams of hydrogen. And what we're going to do is calculate the grams of oxygen needed. So convert this into moles. Use our stoichiometric ratio to show that 2 hydrogens are needed to react with 1 oxygen. And then convert this mole of oxygen back into grams. Alright, let's see how much mass we actually need. So, clear all this out. 10 divided by 2.016, then divide by 2, and then times 32. I see that this is 79.4 grams. Alright, do I have 79.4 grams? No, I only have 40 oxygen. Therefore, oxygen is limiting. All right. This one's going to take one more calculation, more than likely. Well, definitely 2 calculations. All right, I have 10 grams of oxygen and 10 grams of phosphorus. I want to know how much P4O10 I can make. We are going to have to do a limiting reactant, because we got to figure out which one we run out of first, the phosphorus or the oxygen. So since that phosphorus was listed first, I'm going to actually use it first. And 1 mole of phosphorus, according to my periodic table, is 30.97 grams. And my balanced equation says there are 4 phosphoruses for every 5 O2s. And then 1 mole of O2 is 32.00 grams. So 10 divided by 30.97 times 5 divided by 4 times 32 gives me 12.9. And this would be grams of oxygen. Do I have that much oxygen? No. So oxygen is limiting. Alright, but it didn't ask which one's limiting. It wants to know how much P4O10 is made. Alright, we're going to start with the limiting reagent. Going to convert that to moles because that's what we're always going to do with grams. But what we're going to do now with our stoichiometric relationship is relate the oxygen to what we care about. P4O10. And I saved us some time because if you look up there, I gave the molecular weight of the P4O10 of 283.88 grams. So now we take that 10, divide it by 32, divide again by 5, and then multiply by 283.88 to give us that this would make 17.7 grams. So one calculation shows us which ones is limiting. Then we take the limiting reagent to figure out how much of the final number we want, or the final product in this case. Alright, last little thing we introduce in this chapter is theoretical yield. Now, yields are really talking about how much stuff you actually make. Theoretical yields is the maximum amount that's possible to make. Alright, now, where this gets to be weird is percents. We have a desire to get them as high as possible, especially people who go into sciences. They like those A's, so they want these percents really, really high. It causes people to actually cheat in some cases. What I mean by that, let's actually make a calculation with reactants and products, but what we're going to make is, let's do hot dogs, because we need a hot dog, and we need, I don't know how I'm going to draw a bun. That kind of looks like a bun, doesn't it? Alright, and we'd have to put them together. But you know how they're never sold in the same number. Let's say you had, I don't know, 15 buns, and you had 10 dogs. You can only make 10 hot dogs altogether, right? And you're going to have 5 leftover buns. Well, if you were caring about percentages, 10 out of 15, the number of buns you're looking at, that's a terrible percent, isn't it? So, you're actually only using up 66% of your hot dog buns. You're wasting 33% of your food is how that looks like. Well, percents get to be scary because of that. Well, they're not supposed to be in this case. There are times when a reaction can't be 100%, especially not for what you want. I'm going to look at something that organic chemistry students learn early in Organic Chemistry 1. Alright, that molecule right there is propane. So if you have a grill outside with the propane tank, that's the main molecule that's in there. Well, one reaction that we can do in a chemistry lab is react that with HCl. And what's going to happen is, not HCl, I'm thinking of a different reaction. I'm going to react it with chlorine. And what's going to happen is one of these chlorines is going to replace one of these H's, and the other H, is the H that comes off, is going to attach that Cl. So you're going to make some HCl. But then what we're going to see is this weird thing happens. It might replace that H on the end and pop on here. And if it goes over on one of these hydrogens, it's the same thing, just a mirror of it. So there is a chance the chlorine's on the end, and there's also a chance the chlorine ends up in the middle. And we have almost no control over it. That's going to happen in mixtures all the time. Matter of fact, this happens about 33% of the time. This happens about 66% of the time. And there's not much we can do to control those. When it comes to putting in chlorine on a propane like that, that's what you're going to get. Well, if you're an engineer and you need to make a bunch of this thing, here's what's going to kind of stink. No matter what you do, your final yield is only going to be 33%. Because you're going to make a bunch of this stuff that you have no use of whatsoever. And there's nothing you can do about. So it looks like you get a 33%, but if that's all you can get, that's all you can get. Alright, now I'm only saying that on all this page. I want you to point out, I want you to see that 100% is cool, and it's great, and it does happen sometimes, but we're not really going to see that. There's always side reaction, there's always competing reactions, and you never know what purity of a sample you're going to do with. So don't assume a percent is wrong if you get it a low percent. These are allowed to be almost anything. Alright, so how do we get these? Well, it turns out a percent yield, you really just look at the actual yield, which will be a mass, and a theoretical yield, which is also a mass. Now, the theoretical yield will be totally calculated, and then we're going to actually convert that to percent. What I mean by calculated, let's go right to one. Alright, so 80 grams of chromium oxide and 8 grams of carbon are used to produce elemental chromium. We want to know what the theoretical yield of chromium is from those. Alright, you notice how this is a limiting reagent type thing? Because I have 80 grams here, and I have 8 grams here. And I want to know how much of this I could possibly make. That's going to be a theoretical yield. Alright, so very first thing, we need to figure out which one's our limiting reagent. I'm going to start with the 80 grams of chromium oxide because it's listed first. I'll convert that into moles, Cr2O3, which happens the way, let's see, chromium is 52.00, and there are 2 of those, plus 3 times 16, the oxygen. And I get that this has a mass of 152.00. My balanced equation says for every chromium oxide, I need 3 carbons, and 1 mole of carbon weighs 12.01 grams. Alright, so let's see which one's limiting. So 80 divided by 152 times 3 times 12.01 gives us 18.9. Do I have that much? No, I only have 8 grams of carbon. Therefore, the carbon is our limiting reagent. So 1 mole of carbon, 12.01, and every 3 carbons gives us 2 chromiums, according to our balanced equation. And 1 Cr happens to weigh, what was that, 52.00 grams. So what is my theoretical yield of chromium? 8 divided by 12.01 times 2 divided by 3 times 52. and we get a mass of 23.1. Alright, now, if you're actually doing this in an actual lab, and you've weighed out 80 and 8, you would be expecting to get somewhere near that 23.1 grams. Shouldn't be larger than that, because if it's larger, that means you did something wrong, because you somehow made more chromium than you possibly could. That's the largest it can be. Alright, but let's say you actually got 21.7 grams. Alright, with that, we can get a percent yield. We're going to take the actual yield, we're going to divide it by the theoretical yield, 23.1, and turn that into a percent. 21.7 divided by 23.1 gives us this, which is 93.9%. Very, very good percent. More often than not, if we were to do this in our lab, probably our biggest factor is these guys would probably get enough damage from cross-contamination that would hurt our yields. We'd probably get closer to 80, just because there would be things other than just carbon in with that carbon sample. And this definitely would be weird. Although we wouldn't do this lab. Chromium oxide is actually not a good chemical to leave around. Alright, let's do another one of these. Alright, a student prepared potassium benzoate by that following reaction. Given it there, and it's all balanced. If a student used 10 grams of toluene and 7.5 grams of potassium benzoate, what is the percent yield of potassium did the student obtain? All right, you notice how I gave you the toluene, which is the C7H8, and I don't say anything at all about the potassium permanganate, the other reactant. Because it's not listed, we're going to assume it's in excess. Therefore, that is our limiting reagent. So we're starting right away with that. So we have 10 grams of it. And we're going to convert it into moles using the molecular weight. And our balance equation says for every toluene, we would actually make 1 potassium benzoate. And last little conversion, 1 mole of the potassium benzoate weighs 160.22 grams. All right, you notice I haven't used any of this. That's how much we have obtained. That's that actual number they were talking about on that previous slide. So 10 divided by 92.15 times 1 divided by 1 times 160.22, we get a theoretical yield of 17.3. All right, look how little we got by comparison. This is going to be a terrible percent yield. All right, so 7.5 divided by that theoretical yield and then multiplied by 100, this is only a 43.1% yield. All right, that seems terrible, but there are plenty of reasons why it might happen that way. Turns out in this case, this stuff is kind of hard to get to stay nice and pure. So this arrow is definitely a little bit more of a nice little two-way arrow. Some of that simply just didn't react, and there's not much we can do to make it happen. So getting a 43% yield might just be how it is. Alright, that brings us to the end of this chapter. Give yourself some time to spend to work on some sample problems and get ready with it, and send me any questions you have.